So today would be uh lecture 18. Um so in this section we will be investigating vector fields and operators on vector fields and some vector analysis materials. Before we begin, any questions on what we did before or anything related to the take-home projects? Okay. All right. So a little bit of a review is what kind of functions we have been dealing with so far. All right. So we have dealt with real value functions. All right. So it's a function that puts a values on a vector in Rn. Okay, so one example would be the density functions. All right, so imagine you have an object in Rn, right? So that is a subset in Rn, and um, uh, different locations have different densities. All right, so in total, that is a mapping from a subset of Rn to a value in R. All right, that is a real value function. Another kind of function is vector value function. We did before last class. Right? The graph of this vector value function would be a path, right? That maps a value in R into a Rn vector, n-dimensional vector. So an example would be a path, and in certain time stamp you output a position in Rn. Okay, so how about mapping from Rn to Rn? All right, so in that case we will have a vector field for such mappings. So how do we make sense of Rn to Rn mapping? Okay, so for example, in R2 to R2 mapping, so you're mapping from R2 to R2. So basically, what this mapping shows is that in R2 or in a subset of R2, right, we just assign arrows to each position in R2. All right. because a vector can be represented like a arrow in each position. Okay. So in physics, we have a lot of such examples, right? For example, like electromagnetic field, each position will experience a electromagnetic force, which is a vector because it has both direction and magnitude. So like in this case, if this is an electromagnetic field, then in each position you have a force that pushes in this direction with certain amount of push. Right? So for example, in this case, this would have a smaller push comparing to, let's say, in this direction, it would have larger push. Okay. So imagine that this vector field describe the velocity of a particle in a given position. Okay. So if this arrow actually describes the um, moving rate for a um, for a particle in a certain position, meaning that if you drop a particle here, then you have the particle will experience some push in this position to another location, and this another location will have similar vector field that pushes to again to another position. So the particles will go along what the arrows guided it through. Right? So basically, you integrate along this arrow, and the result would be a smooth line. Right? For example, like here, if you drop a particle, let's say here, okay, then it pushes to this direction, this direction, this direction, this direction, all the way again here. And this resulting graph is called a flow line. Right? Such that, right, the velocity vector of this flow line is described by the vector fields F. Basically, the velocity vector are just the vector field F, the vector field F, the arrows in vector field F pushes the particle into having such path. Right? Any questions? All right. What I will show you here is an example in R2. Right. So this is a little project I did before. So imagine this is a two-dimensional um, tube that has that describe the flow of a water, right? So in this case, the flow is obstructed by an object here, right? Imagine this is a rock. So of course the flow would uh, uh, change around this region because the 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 rock um, stops some of the flows and redirect it into another direction. So as you can see, that um, the the velocity around this um, block has changed and become larger, right? The arrow is longer. That means you have larger velocity, right? That makes sense because you kind of pushes the um, the volume in together and have a larger velocity, right? And then when it passes through this obstruction, it becomes flat and um, smooth again, right? So this is an example of a vector field, right? And an example of a flow line would be something like this, all right? So if you have, if you dropped like uh, an object here and you let it flow along this vector field, this is the path that it would go under the flow. Okay? So as you can see, the flow lines are a lot dense than the positions here. That is because you have a obstruction here that kind of pushes through the flows into this area. And after the obstruction, the flows become flat again. Okay. All right. So if a vector field is a gradient of a real value function, then we call it a gradient field. Right? Remember, a gradient takes a real value function into a n-dimensional vector by taking a partial in each component. So you have the first partial with the first uh, component in Rn and put it in into the first position in the n-dimensional vector, and you do the second partial and put in the second position in the n-dimensional vector, and so on and so forth, and into Rn. So for example, in R3, so if F takes a vector in R3 and have some evaluation in R, have f of x, y, z, then the gradient of f is a three-dimensional vector such that you have partial f of partial x, partial f of partial y, and partial f of partial z. As a vector, in terms of standard basis, that would be partial f of partial x times I plus partial f of partial y j plus partial f of partial z k. So if you generalize it into Rn, then you just put generalize it into n-dimensional vector from 3. Right? So such gradient would be a vector field because you input a position here in R3 and you output another R3 vector. So in this case, gradient is a mapping from R3 to R3. Okay. Such gradient field has a property that is hard to make sense now unless you have some sort of vector analysis. All right. So the physical meaning behind this is that if the vector field represent a force, right? Such line interval is called the work done by this force along the path. If the force field is a gradient field, that means no matter what path you integrate along this force, right? So for example, if you this vector field is a gravitational force, so you have then no matter what path you this object goes, the work done along this path will still be the same for path 1, path 2, or path 3. And such value is actually the gradient of the real value function f, right? And you just plug in your endpoints into the function here. This will make sense later on when you take 255 vector analysis. you just have a preview on such thing. So we have a special name for the real value function small f, such that the vector field is a gradient of the small f, right? It's called potential functions. And the value of this potential, I mean, the work done here is just viewed as the difference in potential. So to see that the gravitational force is actually a gradient field is that this is the formulation on the gravitational force, right, by Newton's gravitational principle. Then this actually is the gradient of this real value function f, where the small f has the formula like this. Right? You can verify that when you take the gradient of this, you end up with the vector field here. Okay. So when you look at the uh, the level sets of f, for example, like a gravitational field case, the cases for gravitational force, the level sets are actually the locations such that it has the same altitude. Right? So if the object had the same altitude, it would have the same gravitational potential. Meaning that if you don't change your altitude, then you don't change, your gravitational potential, meaning that if you move along this path, the gravity doesn't do anything at all. You don't change your gravitational potential. The gravitational force doesn't do any work. However, if you move along this path, meaning you change your altitude, that means the gravitational the force will do some work, and you experience some sort of push by the gravitational force, right? So if you have a path like this, right, such that you have perpendicular vector along this um, uh, 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 equal potential sets, that means you go through the direction with the most rapid increase of the potential. So that means this would be the in the context of gravitational force, this would be the free fall, right? That is the fastest way of dropping gravity. That is the highest way of the fastest way of falling from, let's say, a certain height into the ground. Does that kind of make sense? Okay. Of course, there are many kind of gradient field. All right. In terms of weather, then you would have, let's say, for example, it's called isobar, meaning the location with the same air pressure. So of course that if you have vector that goes to the that points to the perpendicular direction, that means you go through the highest increase of air pressure. So that likely would describe the air flows along this direction. That is very likely where the wind will go. Okay, make sense? Any questions? So next we will do some vector analysis on the vector field. All right. So in this case, we'll introduce some operators on this vector field. Right? The first one is called the del operator. So a del operator is of course, like it sounds, it's an operator, meaning it will input a function and outputs a vector in Rn. So for example, like R3 case, so you have a partial of partial x. This is a operator, and you multiply it in by I, the standard basis, one of the standard bases in R3. So similarly, you do that for the partial of partial y and partial of partial z. So when you have the del operator applied to a real value function f, this is the I times partial f of partial x plus j times partial f of partial y plus k times partial f of partial z. Because this is a operator on f, same thing as partial y, same thing partial z. And when you look at this, this is basically the gradient of f. So when the del operator operates on f, you get gradient, right? Right? So in general, for Rn, this is what it will look like. Except in this case, the standard basis is represented like using E1 to En. And this is the operator such that it returns the first partial on returns the first partial. This returns the nth partial. Okay. Any questions? Um, so let's do some example. Let's do example when we do the divergence first. So for divergence is the dot product of the del operator and a vector field F. So because a del operator returns a vector, so this is basically is a vector dotted with another vector. Right. So if we represent the vector field by the component functions, so in each component, you have a component function, which is a real value function. So that means you can apply the operator, the partial, on each component function. So in the first argument, you apply the partial to the first component function. It becomes this. Add the second a partial to the second component function, becomes partial of f2 with partial x2, and so on and so far, and you just add them up. All right. So in this case, the divergent is a real value function, right? It will return to a real value because it's a dot product. So the divergence evaluates a vector in a real value. Right? So let's do some example. So if this is the vector field F, all right, then what are the component function? So the first component function, the component for I is x squared y. The second component function is the component function for j is z. The third component function is xyz. All right. And the divergent basically you apply the first partial on f1. So you apply the partial of partial x here, which is 2xy, and you add to the partial of partial y of f2. Well, in this case, the partial y for z is just 0 because there is no y. Finally, you apply the partial z on the third component function xyz, which you would get xy. So the divergent, basically you add these three things up together, and it becomes 3xy. Okay, so far so good. All right. So in a physics context, if the vector field represents the velocity field of a fluid, right? So in this case, let's see, go back to the vector field here, all right? This represents a flow of a fluid, the velocity of a fluid, all right? The divergent basically tells you about the rate of expansion of this fluid. Okay. So if in the region here that the divergent, if the divergent is 0 everywhere, that means that the fluid doesn't expand or shrink. So in that case, we call the fluid incompressible, which means that the density for this fluid doesn't change along the flow. All right. So such property, such restriction would be useful in terms of in other. Oops. Um, in other physical principle, such as the Bernoulli principle. Right? The Bernoulli principle relies on the fact that the fluid is incompressible. Right? For a such incompressible fluid, it's not here. Oh, different book. Where's it? Oh, here. All right. Oh, right. It's right here. Right. So if the divergence is 0, right, along this vector field, that means in this region, the fluid, when the fluid moves at a certain time interval, it passes through this amount of area, right? This would be the same as the fluid flows to this region in the same amount of time. Okay, so if no no matter the fluid is flowing faster in here or slower in here, the area it travels is the same, right? So that means the fluid doesn't um, uh, expand or shrink because the area is still the same.
And
It's
what
just
are
have
the
a different shape.
last question?
Yeah, sure.
What are the black lines or level curves of big F?
No, no, no. This is the flow line of a fluid, the black line. So the fluid flows in this direction.
And the flow line is interpreted in terms, what's the definition of flow line again?
Flow line is that such that for a flow line, the velocity vector along this path is represented by the vector field. So the vector here is basically the velocity vector for the path. So imagine you dropped a particle here. The particle will move whatever direction this vector field directs it to. So this case, the vector will goes to this direction, then to this another direction here, and eventually it goes to here. Make sense? Because the arrows goes to this direction.
And what's the equation for where's the equation for the flow line or the expression for the flow line? Is it,
Well, in this
it's just
case, I
capital F.
imagine the flow line would be xi minus yj. So the vector field is equals to x minus y. Right? And indeed, the divergence is 0 because the partial x of x is 1, partial y of minus y is minus 1, and you add them up to be 0. Okay. Right.
Thank you.
Um, let's go back. Go back. Oops. The next one we're dealing with is called the curl. Right, so this is the cross product, or instead of a dot product, of the del operator and the vector field f. So of course, cross product only works in R3. Right? So in this case, we are only dealing with R3 vector field. Right. So if you remember, this is how we define a cross product by a determinant of this 3 by 3 matrix. Okay. So when you expand the determinants, it will become the standard basis I times the determinant for this 2 by 2 matrix, which is partial y of f3. So I of partial y of y3 minus partial z of f2. Partial f2 of partial z. This is I. For j, this becomes minus. So minus j times partial x times f3. So partial f3. Oops. F3 of partial x minus partial z of partial f1. So partial f1 of partial z. And finally plus the basis k times partial x of partial f2 minus partial y of partial f1. Right, so this is the curl of f when you expand the determinants. Okay, so for example, if this is the vector field, right, we did before. So again, your f1 is x squared y, f2 is z, and f3 is xyz. So the 3 by 3 matrix for a curl is equal to I, J, K, partial x, partial y, and partial z. And here is f1, which is x squared y. This is f2, which is z, and this is f3, which is xyz. Okay. So we want to find the determinants of this, which is the I times the matrix here, partial y of xyz, which is xz, minus partial z of z, which is 1. So this is for the ith component. Minus for the j component is partial x of xyz, which is yz, minus partial z of x squared y, which is 0. So minus 0. That goes to the j component. And finally, for the k component, partial x of z is 0. And partial y of x squared y is x squared. Okay. So this is the curl of this vector field F. Any questions? So in a special case, all right, if your third component function is 0, so this vector field only applies to R2, for example. So if, let's say, your F2 doesn't have anything on Z, so it's another function of xy. Let's say xy squared, and your, use another color. And your F3 doesn't have anything at all. So in this case, F is basically a R2 to R2 vector field. And let's see what is actually the curl of this F. So in this case, this has to change it altogether. This is xy squared, and this is 0. So for I partial y of 0, basically this is 0 minus partial z of y xy squared, which is also 0. So there is no I component in the curl. For j component, partial x of 0, also 0. Partial z of x squared y, there's no z, so there's also 0. So there's no component in the j direction as well. Finally, for k, partial x of xy squared, this is y squared, and partial y of x squared y, this is x squared. So it does have something in the k component. So in terms of graph, all right, in terms of visual representation, if this is your xy xy plane, the vector field basically is the arrow here. Right? The curl points in the k dimension direction. that is perpendicular to this xy plane. All right. That is the z direction that is pointing out. It's always perpendicular to this xy plane. So what does the curl actually measure? Right. So in a physics context, the curl actually measure the torque of the rotation. So that is when you for example, when you this book doesn't have a good representation. All right, let's use Susan's book. So when you have a flow in a vector field, right, the vector field represents the velocity vector, and the flow line of this vector field becomes a path, right? This doesn't generally describe whether or not the object will rotate or not. For example, if you have the objects here, right, of in this case, it doesn't have any rotation, right? When you go flows back to the original position, the shape, right, the orientation of this object stays the same, right? It still points to this direction, or along this line. However, if there is a rotation in the vector field here, when you when the objects flow along the line, it changes the orientation, right? It points to different location along the line. Right? So this is described by the curl of this vector field. So we call the field irrotational if the curl is zero everywhere. So if the curl is zero everywhere, we call it irrotational. It doesn't change the orientation, or it doesn't have any rotation along the vector field. Okay. So any questions so far for the del operator, divergence, and curl? Right. You encounter this a lot often when you move to vector analysis course 255. So this is just now it's just a little preview on these subjects, right? So in terms of vector analysis, there are two theorems that are relevant here, right? The first is that the a gradient is curl zero. So so that means the curl of a gradient of a real value function, any real value function, as long as it has a second order partial, would be always zero. It will always be irrotational. Why is that? Is that you just apply the definition of curl, right? The curl is the determinant of this 3x3 matrix, right? Except in this case, the vector field is a gradient function, a gradient of a function, which is partial f of partial x, partial f of partial y, and partial f of partial z. Right? You just replace your component function by these partials. Right? And when you evaluate the determinants, right, for I is the determinant of this 2 by 2, so is partial y of partial f of partial z. So you apply the partial y on partial f of partial z. So this is what it becomes, partial f of partial y partial z minus partial z applied to the partial f of partial y, which is here. Same thing for j, same thing for k, and you have the result here. Right? Since our f is a C2 function, the mixed partial doesn't relies on the order of differentiation. So meaning partial f y partial z is the same as partial f of partial z partial y. So these two are the same. So when they subtract each other, it becomes 0. This is gone. This is 0. Same thing here. Partial x partial z is the same as partial z partial x. This is also gone, becomes 0. This is also 0. So the result becomes a 0 vector. 0, 0, 0. Okay. The next one is that the divergence of a curl is 0. So a curl is divergent free. Why is that? Again, you apply the definition on the curl followed by the definition for divergence. So divergent is the dot product of the del operator and a vector field. And in this case, the vector field is a curl. So first, you evaluate what is the curl first. Right? So this is the definition of a curl. And you apply the del operator here. Remember the del operator is partial of partial x, partial y, and partial z. Right. So when you have the dot product, that means the first component multiplied by the first component. So you have partial x applied to this part. Same thing as the second component. So minus partial y applied to here, plus partial z applies to here, the k component. Okay. Okay. And when you expand the parentheses, so partial x applied to the partial f3 of partial y, it becomes of partial x partial y. For f2 becomes partial x of partial z here. So you do the same thing for all the part here. So it becomes something like this. Okay, so again, the vector field here is C2, meaning each component function is a C2 function. So the order of differentiation doesn't matter for all the mixed partials. So partial of f3 of x and y is the same as the f3 of y and x. Right. Again, order doesn't matter. So these two are the same. So when they subtract each other, it becomes 0. So it's gone. Same thing as the f2. Partial x partial z is the same as partial z of partial x. So this is also gone. So finally, for f1, partial y partial z is the same as partial z partial y. So this is gone as well. So the result is a 0. So that confirms the theorem here. The curl is divergence free. Okay. Any questions? We still have a little bit of time. You can ask any questions related to here or related to last class, last lecture, or anything on the take-home project.
Yeah, Professor, actually, I have a question
Sure.
about the take home.
Sure.
Can you go over how the second order partials are solved in the example problem?
Okay. Sure. So for the example, I use a polar coordinate system, right? So in this case, the xy is represented by r and theta. The formula 1 here. So by the chain rule, you will have, you can represent partial theta by partial x and partial y. Same thing as partial r here. Okay. So in this case, you represent partial theta using partial x and partial y. So if you do the other way around, you want to represent partial x by partial theta and partial r. So basically you solve for partial x and partial y. So in this case, you have two equations with two variables, right? So what you want to do here is eliminate the number of variables. So in this case, you go from 2 to 1. You want to eliminate either partial x or partial y. So this case, I chose to eliminate partial x. So first, this is, you just basically treats r and theta and partial theta and partial r as constant. They are just numbers. So you can divide them, you can subtract them, basically whatever it takes to get rid of them. So in this case, I divided by r sine theta in both sides of the first equation. So so that the coefficient before partial x becomes -1. 1 second. right, on the side notes, the homework does count as extra credit, all right, to this take-home project, all right. So this take-home project is an exam. It counts as an exam grade. So when you divide it by r sine theta, the r cosine theta becomes cosine theta over sine theta. So far, so good for the first equation.
Yeah, Professor, I just don't understand the second order partials. I get how you did that, but the second order partials are, I don't really, I don't see how that happens.
Sure. So for the second order, so partial of partial x squared is basically you apply this the partial x twice. So because we have the formulation to represent partial x using only theta and r and their partials, right? Basically, you just plug in this into the partial of x.
You might want to remind us of there was a sign which was supposed to be a cosine, or a cosine which was supposed to be a sine. That sort of
Is right here. I already fixed it. Right here.
I don't know if that was what caused our friend problems.
So this is a typo. In the original file, this was a sine square. It's supposed to be cosine square. So this is the partial of x. So you basically plug in here. Becomes this. And same thing as here. You applied it again. It's right there. All right. And basically you can distribute the parentheses. All right. So this times this plus this times this plus this times this. Basically, this is the FOIL. Right? This is kind of messy. All right. So what I will show you, for example, partial of partial theta of these parentheses, how I expand this thing. All right. So this is partial of partial theta of the first here minus because the partials are linear, so that's why you can do that. Plus partial of partial theta of cosine theta partial r. So this is the first component here. Everyone follows? Okay. Then you have to use the product rule here because this is a function of theta and r, and this is an operator, basically is a placeholder for another function of theta and r. So this is a product of two functions. So when you apply the partial, you have to use the product rule. Hold on a second. Oh, okay. So for the homework, it will have the same deadline as the take-home project. All right, I will move this to the end of 19. Okay. So when you have the product rule here, so that means you apply the partial of partial theta on the function, the first function, which is minus sine theta of over r. And for this part, you leave it like that. So that is the, so remind you what is the product rule. So that is the partial f times g plus f times partial g. So the next one is you apply the partial to the second function, which is a partial. So when you apply the partial theta to partial theta, it becomes the second order partial square of partial theta square. Okay, same thing here. You apply the product rule because this is a product of two functions. So partial theta of cosine theta plus times partial r plus cosine theta times the second order partial theta partial r. Okay, so far so good.
Yeah.
Okay, so next you just evaluate these partials. Okay, partial theta of minus sine theta over r is basically minus cosine theta over r. Of partial theta okay, plus this doesn't change, so basically you just rewrite whatever here. And for this part, partial theta of cosine theta is minus sine theta. Of partial r. And this, you just basically keep whatever this here. All right, the whole thing multiplied by minus sine theta over r. Okay, So that's why you will have a sine theta cosine theta over r square of partial theta. Of course, when you do the same thing here, you have another sine theta cosine. So that's why there's 2. And you have a sine square theta over r square partial of partial theta square. So right there. Okay.
Thank you.
And do the same thing. You should end up with all the terms here. Okay. Any questions? How about the second one, the Kopf-Stuckler production function? If you still have more questions, email me. Feel free to email me. Okay.
I have a question, but
Sure.
not regarding this. I was looking at lecture number 17, but it
17.
appears that it's linked to lecture 16.
You mean the YouTube link?
Yes.
Oh, let me check. Oh, yes. I will fix it pretty soon. This is lecture, yeah, lecture 17. One second. That is strange. All right. So it should be fixed now.
Oh,
The link
thank
should
you.
point to lecture 17. All right. Okay. All right.
So I have a question about the homework, about
Sure.
3.2.
Okay.
And it's just clarifying the problem assignments we need to do. Is it only 4 and 6, or is it?
Wait a second. Let me change the due date first. So for the 3.1, 3.2, so for question 12, oops. So for number 12, basically the question want you to approximate f of -1 minus 1 using the second order Taylor's formula at the point x0, y0 for f. So basically you just need to do number 4 and number 6. Right? Basically you already did that in the previous question to obtain the Taylor's formula. And for number 12, you just use it to approximate the point f of -1 minus 1.
Okay, thank you.
Mhm. Um, in terms of attendance, is hard to keep track in Zoom. So basically, uh, I just look at the roster um, and because the department has asked me to um, kind of count or give the list of students who have not engaged enough in the remote learning platform, and that's what the attendance is meant for. But in terms of your grades, it doesn't really matter, right? I know it's a really difficult time for you in this period, doing lectures remotely. So um I won't give you guys a really hard time in terms of attendance. If there is no question, you are free to leave. The final, it will be cumulative. In terms of the format for exam 3 and final, it will be held in a fixed time window, the same as you do the in-class exam, right? You have a limited time, but in this case, you do it online. I am asking the department to have a platform so that you can just do the test there. But if there's no platform, I still haven't got any reply yet. But if there's no platform, basically you just I post the question um, at the beginning of the exam time. You do the exam and then you scan and upload it on Blackboard. I guess that's the way to do it. It's a little bit tedious, but I guess that's it. You do it by hand, yeah, sure. I really hope there is a online platform that you can just do it online. It would be easier, but if there's no such platform, then you have to do it by hand and scan and upload it on Blackboard. There's some extra work. The final grades. The thing is, uh, the 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 homework grades for exam 1 is for some is still it, as sitting in my office. You I just can't have your final grade until I go to school and pick up your homework for exam 1. So yeah, it's hard for me to get your final grades for exam 1. In terms of the test, yeah, of course you get some extra time for scanning and upload. So basically, I would design the exam to be, uh, 1 hour and a half, and then leave the extra half an hour for you to, figure out the scan and upload thing. All right. Yes, the lowest exam grade will still be dropped. So yes. However, the take-home project counts as exam grade, so that's that. So if your take-home project is the lowest grade, that it will be dropped. The test review. The thing is, because of the break, we lost a lot of class time. We are already, 2 lecture behind. That's why I cut down the exam 2 and 1 more lecture. It would be really hard for us to do a test review. However, if you want a test review, we can do that on the office hour. I still have office hour on Fridays. All right, so today from, what is my syllabus says? I forgot the time. I think it's from 12 to 1, if I remember correctly. Yes, from 12 to 1, using Zoom. I will be using Zoom. It will be a fixed ID, and there's no passcode. So basically, you just enter that ID and Zoom ID, and then that would be the Zoom meeting for my office hour, and we can do test review there. Um, Review sheet. Uh, I will try to do that, but
That question became moot after you said that we could do the review in the office hours. So, but if you have one, that would be great.
yeah, sure. So we can do review session on the office hour. All right. You're more than welcome to come. So for the exam 3 in the updated syllabus, tentatively would be on May the 4th. Oh, May the 8th. May the 8th. So we can do review on that Tuesday, May the 5th. Okay, from 12 to 1. So tentatively, exam 3 will cover the chapter 4 and chapter 5. So everything starting from this Tuesday until the day on that Tuesday. Everything between these two dates and the materials will be on the exam. Okay. So in this chapter 4 is a little bit preview on the vector analysis. All right, we did a vector value function, the path, and its arc length, and all the divergence, del operator, and curl. Right. So in next chapter, chapter 5, we'll be doing uh, iterated intervals. So that means you have integration on dx and dy and dz. Right? That is integration on multivariable. Okay. And how we make sense of it. Okay. You have double integrals and triple integrals, and how we can make sense of this. Okay. Oh yes, the homework assignment for I haven't assigned assignment for chapter 3.3 to 3.4. I would probably get it done by the end of this weekend. You have one more week to do that. Okay. All right. So basically, the homework assignment for chapter 4 and chapter 5 will help you prepare the exam. All right? The exam questions basically are, you know, type of the question you will encounter in these homework assignment.